Alright, well welcome back. So in this section we're actually going to be chatting a little bit about one of these somewhat pesky implementation questions that are going to come up when I actually want to use this notion of this RSA crypto system. So if you remember how this system was built up, we're going to have two players that are going to be in play. We typically identify them as being Bob and Alice. What's going to happen is that Bob's going to be the person that's going to be receiving all of these secret messages, and he's going to have his special little secret decoder on how to actually determine what people are saying to him. So what's going to happen is that he's going to release some public information. So in this case, he's going to release an exponent e, and then it's going to be this modulus n, and he's going to keep his secret little decoder d secret. So what's going to happen is that if I'm this person Alice and I want to send some message to Bob, what's going to happen is you're going to take your little numeric message x, you're going to raise this thing up to whatever that exponent e is, and then you're going to reduce that thing modulo n. What's going to happen is that that new number y is then going to be sent off to Bob, and then Bob's going to take this number y and actually decode this thing by computing y raised to the d, and then reducing that thing modulo n. So you can see in this process that there's two really big things that are going to be happening. Is this idea that Alice is going to have to take this number x, raise it to whatever power e was told, and then reduce that thing modulo n, and n can be whatever it's going to be. So both of those numbers, e and n, can actually be very, very large numbers. So can our message x. So there's this notion of how do we actually compute something like this in a somewhat meaningful and short way. So that's this question of actually how do I do some of this modular exponentiation. So down below you can kind of see this little goal of where we're actually going to try to go to in this case. So initially we're going to look at a few of these somewhat toy examples of actually computing something like 3 raised to the 23rd and then reducing that thing mod 25. I could up the power a little bit to look at 3 to the 98th or 3 to the 300 or 3 raised to the 613th, and again reducing that mod 25. In this case, you could actually do all of those with a pretty simple calculator in that you could actually evaluate what those things all are going to be and then reduce that thing mod 25. That approach, however, is very terrible the moment you actually start increasing these things to becoming somewhat large numbers. For example, if you took something like 3,235 and raised it up to this massive power of 125,000-ish and then try to reduce this thing modulo whatever 2 million, something like that, if you were to just directly compute what that number is, you would have no chance of actually reducing this thing modulo this thing, because that number over on the left-hand side is going to be insanely large. So what I want to do is I want to come up with some somewhat more efficient way to actually compute something like this in a quick manner. This whole process breaks down if I don't have an efficient way to actually compute some of these powers. Because if I have to play this role of Alice, if I don't know actually how to do this, I have no ability to actually send messages off to Bob. Likewise, if Bob is going to have to decode all these things, and it's a very time-consuming process to decode something, he's going to be flooded with an insane number of messages, and he's going to be trying to decode all of these things, and it's all going to break down very quickly. So that's our goal in this case, is we're going to try to come up with a way to actually do this modular exponentiation. What it's actually going to be built on is that it's actually going to be built off of a base 2 representation of that exponent. So for those of you that know a little bit about base representation, the next couple of slides are hopefully a little bit of review. For those of you that may have not seen this notion of how to represent things in various bases, this is a really kind of nice way to see what's going on as you try to convert into different number systems. So in this case, the kind of starting place is going to be this number 37. So I just chose 37 because it becomes a kind of nice number that has a few things going on in this case. So the question here is, how do I actually view this number 37? So this is something you may or may not have actually ever thought of before, but if you dig way back into your world of elementary school and things like this, this notion of the 3 is actually very important. What it's doing is it's going to tell you how many 10s do you actually have. Likewise, that number 7 is going to say how many 1s do you have. So for those of you that remember little tile work, what's going to happen is that you're going to have 10, or you're going to have 3 of these little 10 cubes, or in this case these little sticks that are going to have 10 little squares on them, and they're going to have 7 little individual ones afterwards. So what's going to happen is that you have 3 of the little piles of sticks, and then you're going to have 7 little singletons afterwards. So this notion that 37 is going to be viewed as a 3 times a 10 is going to be exactly that, and then you're going to have 7 of these little singleton 1s. So a way you can view that is you're going to have 3 times 10 to the 1 plus 7 times 10 to the 0. So you're going to have 7 1s and 3 10s. So in this case, 37 is then viewed as 37 base 10. So it's a really weird way to write that thing like there. Typically we drop off this base 10 because typically everything we deal with is going to be this base 10 notion. What I can do in this case is I can start to change things up a little bit and not just deal with this world of looking at base 10. I can actually look at base 5, or I can look at base 3 or base 2. I can actually look at base whatever integer I actually want to see in this case. For example, if I want to look at this thing base 5, what's going to be happening is that I'm going to be looking for all of these multiples of 5 that are going to be occurring inside of 37. So inside of 37, there's a 25, which is going to be this notion of 5 squared. Well, if I take that 25 away from that 37, what's going to happen is that I'm going to be left with a little bit more afterwards. You're going to see that I'm still going to have a 10 hiding inside of there. So it's this idea of that 37. If I break off a 25, what's going to happen is that I'm going to have 12 left over. So that 12 can then be further broken down into a 25 plus a 2 times a 5, because there's going to be essentially a 10 hiding inside of 12, which is 2 5s. And at the very end of that thing is going to be this plus this little 2 afterwards. So what's going to happen in this case is that if I wanted to view the number 37 in base 5, what's going to happen is that there's going to be 125 or 1 5 squared. There's going to be 2 of these 5s, or 2 times 5, and there's going to be 2 times these 5 to the 0, or 2 singleton 1s in this case. So we're always going to be playing with these little 1s at the very end to make up the difference on whatever I have left over, and then after that I'm going to try to break off as many multiples of these 5s as I can. So in this case I could break off a couple 5 squares, or I could just break off 1, I should say in this case, and I could break off actually 2 of the singleton 5s. Likewise, I could look at the number 37 and actually view it in this base 3 world. So what I'm going to be doing here is I'm going to be looking for all these massive powers of 3 that are going to be hiding inside of 37. So in this case, the largest power of 3 that's going to be inside of 37 is a 27. So you can see that 37 is going to be viewed as a 27, and then there's going to be a 10 left over. And then you look inside of that 10 and you're going to try to see how many powers of 3 are going to be inside of that thing, and there's going to be a 9 hiding inside of that 10. So I could view this as a plus 9, and then there's going to be a little plus 1 afterwards. So that 27 is then viewed as a 3 cubed, the 9 is then viewed as a 3 squared, and that 1 is then viewed as a 3 to the 0. So you get this base 3 representation of 37. You can see in this case I didn't actually use any of these just single 3s. So I'm going to have a 1 times a 3 cubed, a 1 times a 3 squared, and a 0 times a 3 in this case, and then finally a 1 times a 3 to the 0. So there's one of these singleton 1s at the very end. So if I wanted to write this thing in base 3, what's going to happen is that I'm going to view this thing as a 1 1 0 1, where that 0 is going to be this placeholder of saying that I don't have any of these single 3s. So the one that we're going to be most important or most kind of interested in is actually going to be this base 2 representation, because that's going to be the thing that's going to make this whole modular exponentiation process work. So the idea is of actually taking some of these numbers and viewing all of the powers of 2 that are going to be inside of that thing is going to be this super important process of actually building these things up from the ground. So if I look at that number of 37, what's going to happen is that I can see that there's going to actually be some powers of 2 hiding inside of it. The largest power of 2 that's going to be inside of that thing is going to be this number 32. In this case, the number 32 is actually a power of 2. It's going to be a 2 to the 5th. What's going to happen is that afterwards I'm going to be left with a little bit of information, and it appears that I actually have a typo in this case, because I know that 32 plus 5 is going to make 37, and I have an extra 2 in this case. So pretend that that little 2 and that little 2 don't exist. So it'll give us some kind of fodder to work with in this case. So in this case, I'm going to look at 32 and I'm going to look at that 5 and try to see how many powers of 2 are inside of that thing. In this case, that 5 can be broken down into a 4 and a 1. So at the end of the day, I see that 37 is going to be a 2 to the 5th plus a 2 squared and then plus this power 1, which in this case I can view as a 1 times a 2 to the 0. So if I want to view 37 in base 2, what's going to happen is that I'm going to view a 37. I'm going to view this thing as having one of these powers of 5. I'm not going to have any powers of 4. I'm not going to have any powers of 3. I do have a power of 2, so it's going to go a 1 there. I now don't have any powers of 1 because I have it by accident an extra 2 in that case. And at the very end, I do have a singleton 1 at the end. So in this case, what's going to happen is that that number 37 is going to be viewed as 100101, and that's going to be viewed base 2. So the big important theorem that comes into play here is that if you give me some number, which I'm going to call an n, I can actually represent this thing base b for whatever base I actually want to deal with in this case. Typically, I'm going to be taking these things as some integer that's going to be greater than 1 in this process. So the idea is that you give me a base b and I can represent any number I want to with that particular base. So the common ones to see, you're going to have this notion of base 10, which are going to be this standard number system that we're used to working with. You can look at the base 2 representations, this notion of binary. You can work at these tertiary ones, which is going to be this base 3. You can work with the base 8 ones, the base 16 ones. There are a bunch of common ones that are actually going to occur along as we're going to work. What we're most interested in is going to be that base 2 one, but because we actually have the nice little theorem statement, we can go ahead and state them for everything, but the one that we really care about is going to be this base 2 stuff. So what we did here is actually going from here's a number, and I'm actually going to try to convert it into its base whatever representation I want to see. But you can also go the other way. So if I give you some number currently written in base 8 or written in base 3 or written in base 2, what you can do is you can always convert that thing back to a base 10 number if you like to think about what that thing is actually going to represent in this case. So if I look at the number 23010 base 8, what's going to happen is that spot right there is going to say how many of these 8 to the zeros am I actually going to be playing with in this case. That number is going to be saying how many of 8 to the 1s am I going to have. So it's going to have a 1 times an 8 to the 1. So that was how many 8 to the zeros. This one's going to say how many 8 squareds am I going to be dealing with. So it's going to be a 0 times an 8 squared. This is going to say how many of these powers of 3 am I going to be dealing with. So it's going to say 3 times 8 to the 3. And then the very last one is going to say how many powers of 4 am I going to be playing with. So in this case, I'm going to have 2 times 8 to the 4th. And if you go ahead and compute that gigantic, massive little number, what's going to happen is that thing simply kicks out 9,736. So if I look at the base 3 one, this is going to be the 0 spot, this is going to be the 1 spot, this is the 2, that is the 3, that is the 4, and that is the 5. So those little things are simply going to become weights. So 1 times 3 to the 5th plus 2 times 3 to the 4th plus a 0 times 3 cubed plus a 1 times 3 squared plus a 2 times a 3 to the 1 plus a 1 times a 3 to the 0. If you go ahead and compute that massive big number, what's going to happen is that it kicks out 421. And just to kind of complete this last one, we'll look at the base 2 one as well because we're going to see that 98 come into play a little bit later. So we're going to have 0 of the power of zeros emerging. We're going to have 1 of these powers with a 1, so that's going to be that little term right there. We're going to have 0 with the squared. We're going to have 0 with the cubed. We're going to have 0 of the power of 4, which are going to be those 3 little things right there. And then the power of 5 and the power of 6, those are each going to pick up a coefficient of a 1. So essentially this thing is just going to be viewed as a 2 to the 6th, a 2 to the 5th, and just a 2. And if you compute that whole thing, it's going to kick out that value of 98. So at the end of the day, what I want to do is I want to come up with a somewhat more efficient way to actually convert from numbers into their base B representation. Luckily for us, we actually do have a very nice little process that's going to come into play. We actually have this base conversion algorithm. And what's going to happen is that it's basically the same thing that we did earlier. What's going to happen is that you're going to try to break off as many of these things as you can. So essentially what you're going to be doing is you're going to just be doing repeats of division of whatever that base B that you have. So if you're looking at base 8, what you're going to try to do is you're going to try to divide by 8 as many times as you can, just resetting that little quotient and that remainder every single time that you go. So if I want to run through just a quick little example of this, we'll play with that number n, which is going to be, let's say, 613. So if I wanted to find the, let's say, base 3 representation of that thing, what's going to happen is that you're going to take this number 613 and you're going to divide it by a 3. So in this case, I know that the number 3 is going to go into 613 and it's going to go into that thing 204 times. And what that's going to do is it's going to leave me with a remainder of a 1. What's going to happen now is that I'm going to take this 204 and then I'm going to rerun this process, again dividing by a 3. So it's a little bit different than this Euclidean algorithm in that I'm always going to be dividing by the exact same thing every single time. I'm still going to be taking this new little quotient and it's going to become my new starting place, but I'm going to be always dividing by the exact same thing. So dividing by 3, dividing by 3, dividing by 3, every way that I go, as I go. Okay, so 204 divided by 3 is going to kick out a 68, and that one goes in there nicely in this case because it's going to leave me with a remainder of 0. And I knew that 3 divided nicely because I know that 2 plus 4 adds up to a 6, and I know that 3 divides nicely into that value of 6. So it does work out nicely in that situation. What's going to happen is that I'm going to take that 68 and I'm going to see how many times does 3 go into that thing. So 3 is going to go into that thing something like 22 times, because 22 times 3 is going to kick out a 66, which is going to leave me with a remainder of a 2, which is then going to say 22 is going to see how many times does 3 go into that thing, and it's going to go in there 7 times, because 3 times 7 is a 21, leaving me with a remainder of a 1. And then next it's going to be 7, and it's going to be a 3. 3 times 2 makes a 6 plus a 1. And then I'm going to look at the 2. How many times does 3 go into that thing? It's going to be 0 times, leaving me with a remainder of a 2. So these little numbers over here that are going to come into play are actually going to form those little weights A0 up through AK in this case. So these little numbers A0 up through my stopping place. So that's what's going to happen here, is that I'm going to view this number of 613 is then going to be viewed as my number with a 211201. And it's going to go in that order as well. This first little number is going to be my A0, and this is going to be my A1, A2, A3, A4, and then finally my A5 in this case. So 613 is then going to be viewed as 211201, in that case, base 3. All right, so what we can actually do is we can actually go ahead and actually make sure that this conversion is actually correct. So what I can do is I can take these little weights, this 211201, look at these little powers of 3 that are going to come into play and make sure that it actually does in fact kick out this 613. So in this case, I'm actually going to jump forward and actually use one of these pre-created slides just to save myself a little bit of time. So in this case, you'll see where I'm going to look at my next example, but what we're looking at is going to be this middle term. So 613 viewed base 3. What I just showed is that it's going to kick out a 211201 base 3. Which is going to say that if I look at this little 1, it's going to say that I'm going to have 1 singleton 1. I'm going to have 0 of the powers of 1. I'm going to have 2 of the powers of 2, so I'm going to have a 2 times a 3 squared term. I'm going to have a 1 with a power of 3. I'm going to have a 1 with a power of 4. And finally, I'm going to have a 2 with my power of 5. So in this case, that's my 0, 1. Here's my 1. Here's my 2. Here's my 3. Here's my 4. And then finally, there's going to be my 5. And if you go ahead and actually compute this gigantic thing, you're going to see that it does in fact kick out a 613. So I do properly see that that is going to be my base 3 representation for that number 613. What you can do in this case, you can do the exact same thing to try to determine what its base 2 or base 8 or whatever base representation you want to deal with. The one we're going to look at is actually this way over on that right-hand side, which is going to be my base 2 representation for this thing. So what you're going to do is you're going to take that number 613 and you're going to be dividing it by 2 repeatedly. So you're going to see how many times does 2 go into 613, which in this case is going to go in there 603, and it's going to kick out a remainder of a 1. What's going to happen next is you're going to have that 6 or 306. You're going to see that 2 is going to go into that thing evenly. It's going to go into it 153 times. So you're going to have a remainder of a 0, and then you're going to continue this process down as you go. What's going to happen is that your A0 is going to be that singleton 1, and then you're going to have an A1, A2, A3, A4, A5, A6, A7, A8, and an A9, which is going to say that this number 613 is going to be viewed as a 100, so 100, 1111, 00101. So you're working it from that way on up. And if you wanted to, you could actually convert this thing back into its kind of nice base 10 representation by seeing a 1 times what's going to happen is a 2 to the 9th. What's going to happen is that that little term, that little 1, is going to go with the 9, 8, 7, 6. So you're going to have a 2 to the 6th as well as a 2 to the 5th. And then you're going to have 4, 3, 2. So you're going to have a 2 squared. And then you're going to have just that singleton 1 at the very end. So if you go ahead and actually compute this big old thing, you're going to see that it does in fact kick out a 613. So that's the notion that we're going to be primarily dealing with, is going to be this idea of viewing some of these numbers as a bunch of powers of 2, this nice little binary representation for these things. So if you're actually used to kind of playing around with this world of Sage and things like that, Sage actually does have a very nice way of actually converting some of these things to whatever type of base representation you want to deal with. What the command is going to be is it's going to be this notion of feeding in this number and then plugging in the word digits afterwards. What you're going to do is you're going to feed whatever base you want to see after that. So if I wanted to look at 613 in a base 8 representation, what you're going to say is 613.digits with an 8 in there. In this case, what's going to happen is it's actually going to be flipped in the order of this thing. So what's going to happen is that it's actually going to kick out the number of 5411, which actually is both annoying and also very beneficial at some point in time. Because what's going to happen is that this is the 0th entry of this list, which is going to correspond to the A0. So when it comes to actually cycling through this list, that's actually going to be the somewhat more advantageous way to deal with that actually cycling. So in this case, you're going to see this 5411. So if I reverse that list, you do properly get this base 8 representation, the 1145. Likewise, if I look at 613 version, this base 3 representation, and then flip that thing, I do probably see the 211201. And if I take the 613 and view it base 2, what's going to happen is I'm going to see that 10011000101, which we do know is going to kick out this value of 613. So if you're not super confident in this world of actually converting bases, that's going to be okay. We're not going to spend a ton of time on actually dealing with a variety of base conversions. What I do really want to know is actually how to take some of these things and view them base 2, which is going to be this idea of how many powers of 2 are going to be hiding inside of some of these things. Once I have this base 2 representation, we can actually then finally go back to this question of how can I actually deal with computing these massive exponents and then reducing some of these things modulo whatever I'm dealing with.